This is video number 23 on probability for actuarial exam P. We're doing question number 64, a modified and extended version of that from what you can find at the SOA website online. We're going to be ultimately determining the percentage of claim sizes for an auto insurance policy that are within a distance of one standard deviation from the mean. Now, we've talked about the mean or expected value of a discrete random variable already. I haven't mentioned what the standard deviation is yet. That's going to be something we need to talk about. We need to define that along the way. In fact, we need to define and find, first of all, something called the variance, and then the standard deviation along the way. When I do these videos, I do more than just solve problems. I give you background information on how to think about things and do things and understand things. And in addition, I often use technology at the end, often with Mathematica. But something else I want to do in this video at the end is I also want to use a spreadsheet. Okay, so we'll talk about how to solve this problem with a spreadsheet as well. So what we have here is a probability distribution for a discrete random variable. It's the random claim size X for an auto insurance policy. It's given in this table that you see here below. This is the probability mass function here, PMF, that we've talked about. Is that really best modeled by a discrete random variable? Maybe it'd be better to model this with a continuous random variable. I mean, we are only using a finite number of values here. Well, that does simplify things. So we're going with a simpler approach rather than a more complicated continuous approach. Part A is to find the mean claim size, also called the expected value. Parts B and C are to do something new, find new quantities that I haven't talked about yet, find the variance of the claim size, and find the standard deviation of the claim size. The mean is a measure of central tendency. The claim sizes are between 20 and 80. The mean might be roughly halfway between 20 and 80, somewhere near 50 perhaps, but not necessarily exactly 50. The variance and standard deviation are measures of spread. Okay, the standard deviation turns out to be easier to interpret. The variance turns out to be a little easier to compute and work with theoretically. Part D, which is the main point of the question that you'll find online, what percentage of the claims is within one standard deviation of the mean claim size? Now, a little rule of thumb is that typically it's over 50% of the claim of the values of the random variable that are within one standard deviation of the mean. Maybe even, you might say, typically close to 68% or so. However, in this case, it's not going to be typical. We're going to have an atypical standard deviation. It's actually going, our percentage of claims within one standard deviation is actually going to be less than 50%, which is kind of an unexpected result. Okay, but that can happen sometimes. All right, so how do we go about solving this here? Well, let's recall some formulas. First of all, there's the formula for the mean. First, the symbol for it is a Greek letter, mu, also called the expected value of the random variable, capital X. Okay, both of these notations mean mean. And for discrete random variables, it's a summation that is often a finite sum, but sometimes an infinite sum. In this case, it's finite because we have finitely many values for the claim size in this case. The values of the claim size, little x, capital X represents the random variable, little x represents its values, times the values of the PMF, probability mass function. So we need to do that kind of summation. When we've got a table like this, it's most natural just to extend the table with, say, products of x times p of x in a new column, and then just add those numbers up. We can get the mean pretty quickly. Let's go ahead and do that. So the new column here we're going to have is x times p of x. 20 times 0.15 is going to be 3. 30 times 0.1 is also 3. 40 times 0.05 is 2. 50 times 0.2 is 10. 60 times 0.1 is 6. 70 times 0.1 is 7. And 80 times 0.3 is 24. Right? Add those numbers up. 3, 6, 8, 18, plus another 13 is 31, plus 24 is 55. The mean is 55. We've done part A. Okay, we found the mean claim size, and I said it might be close to 50, not too far away from 50. All right, so what's part B? This is something new. And I actually want to do this in two ways. One based on a definition, and one way based on a manipulation that often results in an easier calculation. So the definition of the variance of x var x is a typical symbol for the variance, or maybe just v of x for short, is an expectation. We've talked in recent videos about alternative kinds of expectations. For example, something we call the second moment, the expected value of x squared, a couple videos ago, and the expected value of a transformed random variable in the last video, video 22. This is a transformed random variable. What transformed random variable is it? It is capital X minus the mean of capital X quantity squared. Okay? Why is this a measure of spread? Think about it intuitively. First of all, it can't be negative. This is going to be an expected value of a squared quantity, and we're not dealing with any complex numbers or imaginary numbers here. A squared quantity has to be greater than or equal to 0. The mean of such a squared quantity can't be negative. Okay? Why does it measure spread? Well, think about it intuitively. If x takes on a value far away from you a lot, then these differences will tend to be far from 0 a lot, either positive or negative. When you square them, they get even farther from 0, assuming those differences are bigger than 1 in absolute value. On the other hand, if the differences tend to be small a lot, probability-wise, then these differences, then the squared values are also small. Relatively speaking, we can expect an expected value that's small. Does that make sense? So that's an intuitive reason why this seems like a good idea as a measure of spread. As an expected value of a transformed random variable, we still use the same PMF, but we alter what gets multiplied. We need to multiply this quantity times the PMF values. Instead of a capital X, we use a lowercase x because these are the values of the random variable. Mu turns out to be 55. We found the mean. We use the mean now. Okay, so let's go ahead and do this sum. Again, let's extend the table. So we want the values of x minus 55 quantity squared times p of x. A little bit more unpleasant of a calculation, but let's go ahead and do it and use the calculator here. So the first value of x is 20. 20 minus 55 is negative 35. Negative 35 squared times p of x is 0.15. So negative 35 squared is the same as positive 35 squared. 1225 times 0.15 is 183.75. For the next one, we have 30 minus 55 squared is negative 25 squared, which would be 625 times 0.1. That's going to be 62.5. For the next value of x, 40. 40 minus 55 is negative 15. Negative 15 squared is 225. That needs to get multiplied by 0.05. 225 times 0.05 is 11.25. Hang with me here. I know this is not pleasant, but it is important to see this at least once in your mathematical life. Next one, 50 minus 55 is negative 5. Negative 5 squared is 25 times 0.2. That will be 5. Then we have 60 minus 55 is 5. 5 squared is 25 times 0.1. That will be 2.5. 70 minus 55 is 15. 15 squared is 225 times 0.1 is 22.5. And finally, 80 minus 55 is 25. Square that, you get 625 times 0.3. 625 times 0.3 is 187.5. So the sum of these values should be the variance of the random variable. Let's go ahead and, I've already got 187.5 in my calculator, I'll just go upward here. Plus 22.5 plus 2.5 plus 5 plus 11.25 plus 62.5 plus 183.75. The variance is 475. That's what can go right there, 475. Okay? It's a number, a non-negative number that is somehow a measure of spread. If you had PMF values that were not so big at the extremes at 20 and 80, if these two numbers were smaller and these numbers in here were bigger, you'd be more likely to get values of x close to the mean. We'd expect a smaller variance. Okay? if these numbers at the extremes were smaller and these numbers inside were bigger. They still have to add up to 1 because it's still got to be a valid discrete random variable probability distribution. I do want to show you again an alternative way to calculate the variance, but let's solve part C and part D first before we go back to that. Okay, the alternative, hang with me though, the alternative way of doing it is just as important as the definitional way. In fact, you might even say more important because you'll use it more often. This calculation can be kind of a pain sometimes, especially if the mean is not a nice number. We had a nice mean, but if this were 55.23678 or something, then this calculation would be a little bit more of a pain, especially by hand. Let's go ahead and solve part C and D before we talk about that alternative way of doing it though. Part C is to find the standard deviation. Well, that's easy. The standard deviation is the square root of the variance. Okay? The variance is sometimes labeled with a sigma squared because the standard deviation is labeled with a sigma. Okay? That's why the variance is labeled with a sigma squared. It's the square root of sigma squared, which is the square root of the variance, the positive square root. Okay? We don't want to do a plus or minus here. This is the square root of 475, and that is about 21.7945. 21.7945. That's the standard deviation. That's also a measure of spread. If again, these probabilities at the extremes were smaller and these ones in here were larger, not only would we get a smaller variance, we'd get a smaller standard deviation. All right, now the problem itself, part D, what percentage of the claims are within one standard deviation of the mean? Mu plus or minus sigma would be the two extremes. 55 plus or minus 21.7945. 55 minus 21.7945, see if I can do that in my head, that would be 33.2055, I believe. 55 plus 21.7945 would be 76.7945. Okay? What percentage of the claim size values are between these two numbers? Meaning they are 40, 50, 60, or 70 are the ones that are between those. You got to add up these percentages to get the answer to part D. 5% plus 20% plus 10% plus 10% is 45%. That is the answer. That turns out to be choice A on the sample exam, and it is less than 50%, which is unexpected. Typically, with most distributions, 50% or more are within one standard deviation of the mean, and in fact, commonly it's close to 68% as a number you'll see a lot. Actually, on the sample exam questions, 68% is one of the options, sort of maybe to mislead people or to make them hope that they don't actually have to do the calculation here. The 68% occurs with something called normal distribution, which we'll talk about later. But this is the answer, 45%, a little bit less than 50%. All right, so now we want to talk about this alternative way of calculating the variance, which in general is a better way. And then we want to look at the technology, both the spreadsheet and Mathematica. I would highly recommend trying to stick with me here. This is pretty important stuff. Okay, let's look at this equation here for the variance. So again, the variance of x by definition is the expected value of x minus mu squared. In fact, what I'm about to do right now is probably the most important thing here. What we want to do is we want to rewrite this expression using properties, really important properties of expectation. First of all, go ahead and square this. X minus mu squared is going to be x squared minus 2x mu plus mu squared. What can we do with this? Well, it turns out that the E here, the expected value operator, which takes a random variable and gives you a number, is what's called linear. It satisfies a linearity property. The expected value of a linear combination like this, differences and sums, is the corresponding difference and sum linear combination of the expected values of the pieces, this, this, and this. I'll write it out here. This is the same as the expected value of x squared minus the expected value of 2x mu plus the expected value of mu squared. The expected value of a linear combination, a combination of quantities with summations and differences and constants like the 2, for example, is the corresponding linear combination with the same coefficients here, 1, -1, and 1, that I had up here, 1, -1. I mean, I could have thought of it as a -2, and in fact I can factor the -2 out, and a 1, like that. I'm not proving this at the moment, and in fact to prove it in its full generality is actually kind of challenging. It requires some multivariable calculus, you might say. When we're dealing with just one single PMF, it's not so bad, but I don't want to get into it here in this video. It'll make this video too long, and it's long enough as it is. We need more properties of expected value, the linearity properties. The 2 and the mu here are constants that can be pulled out in front. That's also a linearity property. To write it like this. And I can also simplify this thing. This is the expected value of mu squared. But wait a minute, mu and mu squared are just numbers, constants, constant random variables? Yeah, you could think of them that way. What's the mean of a constant random variable? A constant random variable always equals that constant with probability 1. Its mean will be that constant. In other words, the expected value of the constant mu squared is mu squared. That's because mu and mu squared are constants, 55 for mu and 55 squared for mu squared. Now look at this thing right here. That's the expected value of x. That's the mean of x. That's mu itself as well. So what I have here is the expected value of x squared, the second moment of x, minus 2 mu squared plus mu squared. This is the same as the expected value of x squared minus mu squared. Or if you prefer, the expected value of x squared, the second moment of x, minus the first moment of x, quantity squared. Okay? And again, this has to be non-negative here, greater than or equal to 0, so therefore this has to be greater than or equal to 0. And that means the second moment is always greater than or equal to the first moment squared. Okay? That's actually a pretty important fact. All right? So this expression here is the computational formula for the variance. It is, if you're going to do it by hand, even with calculator help, typically the best thing to do. Okay, this calculation here quite often is nastier, especially if you're doing it by hand. Now with technology, you really could do it either way, and it's not a big deal. Let's confirm that we get the same thing that we got before. So let's make a column of values of x squared. 20 squared is 40. Okay, yeah, let's go ahead and do that. 20 squared is 40. 30 squared is 90. 40 squared is, 20 squared is 400. 30 squared is 900. 40 squared is 1600. 50 squared is 2500. 60 squared is 3600. 70 squared is 4900. And 80 squared is 6400. That's the values of x squared. What about the values? We want to go after the second moment, the expected value of x squared. I need to multiply these by the PMF values as well. 400 times 0.15 is going to be, 60. 900 times 0.10 is 90. 1600 times 0.05 is going to be 80. 2500 times 0.2 is going to be 500. 3600 times 0.1 is 360. 4900 times 0.1 is 490. 6400 times 0.3, what will that be? 640 times 3, that'll be 1920. Double check that here. 6400 times 0.3, yep, 1920. Now add these to get the second moment. Not the variance. It's a common mistake to calculate the second moment and think you've calculated the variance. No, you've got to subtract the squared mean from the second moment. So 1920 plus 490 plus 360 plus 500 plus 80 plus 90 plus 60. The second moment is 3500. So the variance, combining these two things, the variance is 3500 minus the mean squared minus 55 squared. 55 squared is 3025. Subtract that from 3500, you are going to get 475, just like we got before. And again, the square root of the variance is the standard deviation, and then you think about this kind of thing to figure out the answer to the question. All right, that's a lot. Let's go to technology now. Let's do a spreadsheet first. This is worthwhile. To confirm the answer, you should be able to find these things with a spreadsheet, and then I'm going to show you Mathematica. We'll do the Mathematica real quick, okay? The spreadsheet will take a little bit longer. If you haven't used a spreadsheet before, what we have here is we've got the random variable values, the values of little x, the PMF values, probability mass function. To find the mean, we need to find these values and add them up. So with the spreadsheet formula, what you can do is use the cell references. First of all, use an equal sign like you see here to make sure it's going to do math. Then take what's in B5 and multiply what's in C5. That'll be 20 times 0.15, that'll be 3, like we got before by hand. And then the magic of the spreadsheet is you can copy and paste this formula downward. We can click and drag this to find all these products. For example, 60 times 0.1 is 6. The formula gets updated, okay? And that's what you want typically, though there are some times where you need to make adjustments to that, and actually I'm going to show you that. If we calculate a sum of these things with a function equals sum for sum and highlight all these numbers, that'll quickly add them up to get a mean of 55. Okay, there's the mean, 55. Let's calculate the variance and standard deviation with the spreadsheet both ways. Actually, I'm going to do it the second way first. That's the computational formula. I'm going to calculate these quantities and add them up, and then subtract the sum, which is the second moment, subtract the squared mean to get the variance. So the values of x squared are, in this case, the formula would be equals b5 squared. We'll calculate 20 squared, which is 400. Click and drag or copy and paste. These are the values of x squared. The sum of these is the second moment. Let's go ahead and label it that way. And I don't have to retype equals sum. I can just copy and paste this over. And that is, no, that's not the second moment, sorry. I made a mistake there. I need to multiply by the probabilities. Sorry about that. I do make mistakes. I need to multiply by the probabilities before I add, so I need to take this times this, copy and paste or click and drag, now add to get the second moment, which is 3500. The variance is the second moment minus the first moment, which is the mean squared. So this should be the 475. Yep, and the standard deviation is the square root of that. You can do equals SQRT, or you can raise that thing to the 1/2 power, like this, about 21.7945, like we got before. Let's compute the variance in this with the other formula, the first formula that I showed you that I called the definition. Let's just go ahead and do it all at once here. The value of x is here, minus 55. I can just type 55 in, but I can also use the cell reference D13 if I use $signs like this. That'll keep the cell reference absolute or fixed as I copy and paste downward. It won't change. The dollars don't mean money here. And the PMF values are right here. So this should be, yes, x minus mu, which is again 55, quantity squared times the corresponding PMF value. And again, the D13 will not change as I copy and paste downward, which I don't want it to change. The sum of these things will be the variance. This will be 475 right there. Okay? So that's how to use a spreadsheet to calculate these things. Let's go to Mathematica now. I am showing you something new in Mathematica here. I've showed you how to do probability distributions in simulations before, but here I need what's called an empirical distribution built into Mathematica. What I have here is a way to get Mathematica to generate this distribution that is not described with a formula really. The PMF is described with a table. Here I've got the values of the PMF, and then I need to put an arrow, and here are the values of x. This code will enter this distribution into Mathematica's memory, and then if I want to do a simulate sampling from this distribution, I can use something called random variate. This will generate 100 sample values from this distribution, 100 claim sizes, you might say. And it is a sampling kind of thing. If I redo this, I get different numbers each time. it's a simulation. But no matter which one I do, you should expect about 15% of them to be 20s, 10% to be 30s, 5% to be 40s, 20% to be 50s, 10% to be 60s, 10% to be 70s, and 30% to be 80s, okay? Look over that. Are there about 30 80s? Probably. Not exactly necessarily, but close. Let's do it 10,000 times instead of 100 times, though I don't want to see 10,000 numbers here, so I'm using a semicolon to suppress output. I can make a histogram of the data. So this is essentially a simulated PMF almost, although I got to divide these numbers by 10,000 since I did 10,000 sample size 10,000. But you can see there's about 30%, 3,000 out of 10,000, 80s. About 20% 50s, because this is 2,000 divided by 10,000. Just like we had a 0.2 there corresponding to the 50s right here, etc. Okay, these are approximating those probabilities if I divide all these heights by 10,000. I can calculate the mean, variance, and standard deviation both for the theoretical distribution and for the simulated data. So the mean of D is going to calculate the theoretical mean, which is exactly 55. The mean of the data is going to calculate the average of the data that I generated with these things. An actual arithmetic average where you add the numbers up and divide by how many you have, it won't necessarily be exactly 55. Probably not. Yeah, close, but not exactly. The variance, this should be exactly 475. The variance of the data should be approximately 475. Standard deviation of the distribution should be about 7945. Yep. And the data standard deviation should be close to that. Okay. So a lot of stuff in this video, a lot of important stuff if you want to have success in understanding probability. Thank you for sticking with me in this long video.